been trying it. It's not working.
I'm not even a coffee person, but I feel that it's necessary in these circumstances.
I'm a huge coffee person, and I have yet to up my intake because I think that would actually cause me to take more time in interviews.
Yeah.
So,
see, I felt pretty good about this interview because filling out all these applications requires a lot of soul searching, and I was like, okay, pretty much thought of everything I need to, and she was gonna ask me questions.
You know your soul?
Huh?
You know your soul?
For the most part. And so I was like, okay, I'm ready for this I'm ready for this interview. So I went to Mr. Catlett just to get some more input on it. And he said, what color is your brain? And I was like, what? And he said, what color is your brain? And I said, I'm going to guess pink because I've seen a lot of diagrams and it's pink in all of them. And he said, that could be an interview question and that's not how you want to answer it. And I was like, what? So apparently I'm supposed to say like an actual color and then explain something about myself. So like my brain is red because I'm passionate about the stuff I care about and I'm a hard worker when I'm trying to achieve my goals.
That sounds made up.
That is made up. You
Exactly.
can't physically change the color of your brain based on your personality and traits that you've acquired. That's basic biology right there.
And then Mr. Stark asked me, he said, what would you do if you were shrunk down and put in a blender? And I was like, what the heck are these questions? My thought was I was going to stand on the little middle part that just spins, but there's no blades there.
But then you have the centrifugal force that would fling you across the edge and knock you out.
I'll hug the center.
All right, you hug the center.
But apparently the correct answer was that something about my body weight proportions would allow me to jump out of the blender. So I could just jump out. But I don't understand. I would still be just as weak. I'd just be smaller. He said that that would be an engineering question, which is sad because I'm
Wouldn't
going
they put the lid on the blender though?
Huh?
Wouldn't they put the lid on it though?
I wouldn't put a person in a blender and then not put the lid on.
That's what I'm saying.
Come on.
Come on, Stark. What the heck?
Yeah. And the woman I'm interviewing the woman who's interviewing me works at Wake Forest, and she was like, cancer, but she was at MIT. So she knows a little bit about the field I'm going into, which I don't like. Because what if she tries to ask me questions about it, and I'm just like, I don't know. That's what college is for. I'm supposed to know this stuff after that. So now I'm really good about that.
I don't think they're going to ask you what color your brain is.
I really hope not. And Mr. Catlett said, well, sometimes there will be like this really smart person, but they're kind of quirky. And I was like, please let that be her. I can identify more. And I wouldn't consider myself quirky, but I certainly feel talking to someone who's quirky over someone who's really proper and wants people to be perfect.
I'm quirky.
Yeah, absolutely. And I spoke
my lord.
I don't think he's quirky. Like, he'll just say stuff when there's nothing. Like, I'll just be doing homework and he walks upstairs and goes in the room and says, what? I don't know why he chooses that a lot. He says that quite frequently. I felt really good about calculus. Yes, now I forgot what we did.
Oh my god, it's so bad at this book. There were some of them where it took me like 20 minutes to get it. I actually was able to get it. Others I just couldn't even get it. And then it's all I just looked at it. This is literally one of the rules that's like 4 pages back.
Yeah.
And they're right next to each other. That made me really mad. I'm like, maybe teach this to me. It was bad.
I really wish I had motivation for this semester though. I just actually applied myself in this class. Like, I tried my best to get good grades, but I'm not willing to do extra stuff. And That's
hours.
really unfortunate. Because I feel like I could have done a lot better in this class.
Yes.
I don't think I could have done any better.
But at the same time, I'm at the point in
Now,
my
that
senior year,
is what we can't.
and that's really unfortunate for someone who's trying to get good grades.
Oh, I have a question. For the course evaluation, are you evaluating me, Mr. Gaddis?
That's
Is
good.
it teaching like that you're teaching?
I'm like, yes, but I'm not going
Was it Mr. Gaddis' evaluation on the Isothermal noodle?
Yeah, maybe.
to do the future of the.
Yeah, I just wouldn't do
Reason
it
took
for
the
this.
elevator, now he's
I
on the
don't do it
stairs.
for
Right.
I did it, but it's
It's
like,
like,
I'm
so
so
much
bad.
and sure.
Do you like Fox?
Reason said he was taking the elevator.
Did it get stuck? There he is.
Nice. Actually, money. Are you saying I can't because I'm food and nothing? Where's that from?
Huh?
Oh, McDonald's.
Yeah.
Do you like their coffee?
You can hear the J.
McDonald's as a whole, but they have good coffee.
The video from yesterday, it's finally available.
What color is
I
your
don't,
brain?
I don't know if it's the quality or maybe they were short staffing. Yeah.
It's made out of gray matter.
It's supposed to be more of a creative
I'm
question.
British.
That was a question they could ask me in an interview.
What? What question?
Oh,
Color's your brain
what
and
color
why?
is your brain? Rainbow, because I'm gay. Is that the appropriate answer, Sam?
Quit. I quit.
I mean, what would you say?
Hey.
I realized they probably heard all of that.
That's okay.
Yes, we did.
Yeah, that's why we're laughing.
I mean, it's a pretty dumb question, let's be honest.
It's gray, right? Or is it pink?
A dumb answer for a dumb question.
Well, my answer to the question was it's pink because I've seen diagrams and it's pink. And
And
Mr.
it's
Catlett's
gray
like, that
when
is
it's
not.
dead?
That's so uncreative. Do the gay thing.
Mr. Catlett was the example. I was thinking my brain is brown because brown is the color of the mundane. And I am punctual and dependable.
Oh my goodness.
Why? Do you want to broadcast yourself as mundane?
My brain is green for life.
Just say golden. I'm descended from the gods. I'm like related to Zeus. That's more creative.
I did give up, but it was definitely. Yeah.
What color is your rainbow?
That's the thing that's like.
Have you ever tried to eat soybeans in your bed?
That's an oddly specific question.
Yeah,
I'm
it's
guessing
pretty.
you have.
Yeah, it's not easy.
Wouldn't eating laying down not be easy in the first place?
Well, you kind of sit up when you eat in bed.
Okay,
You ever
what-
had breakfast in bed?
Yeah, but I didn't eat soybeans for breakfast.
Yeah, you're right. I mean, I don't know what you eat for
Wait,
breakfast.
was that an interview question?
Yeah, yeah,
Have you ever,
Sammy.
have you
Sammy.
ever eaten
Soybeans in
I-
bed.
Yeah.
Oh, yeah, that's
Yeah.
tomorrow. Wait, so what time are you leaving Phoenix Friday?
12. To give
12.
myself 3 hours, like, nighttime.
You should just go
Yeah,
to the Phoenix.
in person.
Then she'll have to make it up.
We better do
Just
that.
straight up digit, dude.
No.
Okay, well,
Yes. Yes, you
don't
can.
wanna
about that time. We already have a request, one problem in section 4.5,
Yes.
4.5, so.
No, you don't.
Study for the exams I've already taken at that point.
Ah.
Here, remind yourself of calculus and how
I
well
don't think so.
you did on that. I
Are you guys studying
Okay,
individually
so
the whole time?
we're gonna take a look at it now, problem 45 on section 4.5.
Gail
And,
is speaking.
That was the request already. So let's see, 1 over 39 minus x squared here. Oh, here.
Got him. Got him good.
The book apparently gives an answer involving inverse sine. We want to see how we can get that. I'm just kind of thinking, I'm just going to say, we know we need to use the fundamental theorem of calculus, which says we just need to find the indefinite integral, which is the antiderivative of this function, and then evaluate at the endpoints of the function. The question is, what's the antiderivative? And we've gone over before that the derivative of inverse sine of x is 1 over square root of 1 minus x squared. So that looks a lot like this, but not exactly like it. So what could I do is the question, how can I modify this one so that it looks like that? Well, let's try something. I don't know what if I factor out a 9 on it? Let's try that. Let's take 1 over the square root of 9 minus x squared equals, and if I factor a 9 out of that denominator, let's see, that gives 1 9 times 1 over the square root of 1 minus. If I factor out a 9 out of the square root of it, it's the square root of 9. So then this is x over 9.
Oh no.
Maybe x squared over 9. Then that could be 1 over 3 times 1 over the square root of 1 minus x over 3 quantity squared.
You know what? I don't know.
That did how to get to it, yeah. So
What's the sign inverse of x over 3?
this expression and that expression are equivalent. Simply by factoring out a square root of 9 out of here, you got square root of 9. How can I use that?
Would it be 1/3 sine inverse of x over 3?
Let's see. Yeah, let's try that and make sure. It sounds reasonable. 1/3 inverse sine of x over 3. So I take the derivative of that. I'm not sure we need this 1/3 because that's going to be real close. That would be 1/3 times derivative of inverse sine is like this. That's 1 over square root of 1 minus x over 3 squared. But because that's not simply an x, I have to take the derivative of that x over 3. So times the derivative of x over 3. Chain rule, high rule, for example. So, well, what is the derivative of x over 3?
1/3.
This is itself 1/3. So I don't,
Oh,
that gives me the 1/3 I needed, so I didn't need this 1/3. So if we take off that 1/3, take out that 1/3, now we've got it. We've got 1/3 times 1 over the square root of 1 minus x over 3 squared, which is equal to all the way back to here.
Got him.
All that? So the derivative of this gives me this, which is in fact, we've shown right up here, this expression here is equal to 1 over square root of 1 9 minus x squared. In other words, if you took that 1/3 multiplier that's right there, if you took that 1/3 multiplier and distributed it back in, you would get back to this. So that tells me that the antiderivative of this is inverse sine of x over 2. Want to follow all that thinking?
Yeah.
That one wasn't quite as obvious, but with a little bit of fiddling around with algebra, you get there. The hard part was probably recognizing that you could factor out square root of 9 out of this. So now it's plug and chug.
The greatest.
Inverse sine of plugging in the 3/2 gives me a 1/2 minus inverse sine of 0. Well, let's see. Sine is equal to 1/2 at an angle of 1/6 pi. Sine is equal to 0 at an angle of 0. Is everything okay over there at Davidson?
Yeah. Yeah.
You just heard a lot of rumble or something. Was there something happening, or was it just?
Housekeeping.
Gotcha.
Custodial duties.
I didn't know if you were having maybe a earthquake or something. The whole building was rattling, but it sounded like over here. Okay, so everybody follow that. I walked back away from it, but everyone follow that. Davidson, we can move the camera, but you follow this. Questions on this one now?
Got him.
Okay. Other questions on the homework? Maybe one more or something, anybody? Fine, and just kind of stuck on this section 4.5.
Oh,
Can you do 61?
yeah, or 59.
61. Yeah, let's take a look at it.
Yeah,
Oh my gosh.
Oh my, what is it?
what number is it? 61. 61.
It's a piecewise.
Why, that's right. So let me see if I can get a copy down correct first of all.
Hey, do you want to get snaffled today? Yeah. That's the right attitude.
Okay, so the directions gave you a hint. When you get to the ones with the absolute value, you have to deal with it as a piecewise. And let's make sure we understand what that means. So for a moment, I'm just going to ignore the absolute value just for a moment. And if you were going to graph y equals 2x squared minus 5x minus 3, you might think of it as 2x times x minus 3 and plus 1, I guess, something like that. So with that in mind, this has an x-intercept that looks like a -0.5, and another x-intercept at 3, and it's some kind of parabola shape, so positive coefficient, so it looks like maybe something like this. Y'all with me there? That's just a rough sketch of a function without the absolute value. What does it mean graphically if you put the absolute value on it? So if I were to now graph y equals absolute value of 2x squared minus 5x minus 3, just graphically, what's that going to
W. It's going to look like a W.
Yeah, all of the y values will now have to be positive. So that means it comes down here, and it comes back up like this. And you've made all the y values magically positive by the absolute value set. Now, how are we going to be able to use that in calculus? Well, that's where the piecewise function idea comes back in. So remember that the definition of absolute value of any number a is equal to, by definition, what?
Plus or minus a.
Piecewise function.
Plus or minus a. Plus or minus a.
Yeah, it's either going to be a or the negative of a, depending on what?
If x is greater than 0, and if x is less than 0.
Well, there has to be an equal to. Wow.
Okay, so that was the definition of absolute value as a piecewise function. So we can use this concept here to break up this function into a piecewise function. It appears that the a, which is the inside of this stuff, is already positive when we're left of -1/2, and when we're right of +3. But the inside of this is negative when we are between -1/2 and 3. So this function here could be rewritten as piecewise function is going to be, we do the left end first, it's going to be just the positive of it because it's already positive. If x is less than or equal to -1/2, it is the negative of that if x is between -1/2 and 3, and it's the positive of it, it's already positive, if x is greater than or equal to 3. So there's f of x as a piecewise function for the absolute value function. Clear on this? So this allows me to not have absolute values in my function by breaking it up into pieces. I no longer have the absolute value symbol. And because the intervals are defined at endpoints, I can split up my definite integral according to those endpoints.
Oh, that makes sense.
So I can go from -2, so the region of interest for me right now is from -2, which is there, up to 4, which is there. So I'm looking at the area under this curve, plus I'm taking all this negative area and I'm going to make it positive area, and then this area here. So I'm just going to look at the area in 3 sections. So from -2 to -1/2, I'm left of this point, so I'm above the axis. So I'm using this function. So I'm just doing 2x squared minus 5x minus 3. And then plus, the next section is from -1/2 to 3. But now the original function is below the axis, but to put the absolute value on, I got to take the negative of it to put it above the axis. It's negative of 2x squared minus 5x minus 3. and then plus 3 to 4, a positive of it. So 2x squared minus 5x minus 3. So you just have 3 pieces to add up. Each of them are very similar, and the antiderivative is the same except for a minus sign. It's not too difficult to do after that. We all understand the thinking there? We're trying to get the area under an absolute value function, which is going to be all positive area. And so we had to handle it, we had to break it up using the definition. The rest is, we can finish this out. The rest, since this is polynomial, this is fairly easy to find the antiderivative of. So I'm just going to go right to the antiderivative. Let's see. Antiderivative of that. Let's go through it. What is the antiderivative of
2/3 x cubed?
No.
Come on, man, that's it, right?
No, it's 3 halves x squared. Or no?
No. It's
Just
cubed.
kidding.
Did you guys like it?
Cubed.
Because
Oh,
you
I
can
dropped
have
the
one.
squared. Huh, just kidding.
that? Is 2/3 x. You're right, Rachel. 2/3 x cubed and minus 5 halves x squared minus 3x. Power rule for antiderivatives.
What do we need to see?
Raise the power 1 and divide by it.
Yes,
And then this is just going to be the same thing, but the opposite of it. So it's going to be negative 2/3 x
Why
cubed
did you see for it?
plus 5 halves x squared plus 3x from negative 1/2 to 3. And plus, and this is going to be back to the original, so 2/3 x cubed minus 5 halves x squared minus 3x from 3 to 4.
Got him.
Then you plug and chug your numbers.
Mr. Gaddis,
That's right.
why don't we write C's for these antiderivatives?
So that's an excellent question. An excellent question. The second period class asked that question yesterday. So the question I think if I'm understanding your question correctly, we are doing this fundamental theorem of calculus, and we are then finding the antiderivative, the indefinite integral, evaluated from A to B, and we defined the indefinite integral as capital F of x plus c. Now remember this? So strictly speaking, that's the definition of indefinite interval. Is this correct there? If that's what he was inferring, and I think that's what he was. And so why aren't we putting that c in there? Well, there's 2 reasons. Reason number 1 is the theorem, the fundamental theorem of calculus said, let f of x be an antiderivative.
Oh.
Well, it's a singular antiderivative. So in that case, I could choose my c value to be any of the c values. C can be any number because you're just getting a parallel set of curves. What if I pick c to be 0? That's perfectly good. I could pick c to be 17 if I want. I just need 1 in the theorem. But if you wanted to include the entire family, okay, let's watch what happens. If you evaluate, you're going to get f of b plus c minus f of a plus c. The c's cancel. It doesn't matter what c value you pick is the point. So once again, since it doesn't matter, then we can just have any one antiderivative will work. And let's pick the one with c equals 0. It's a good question. Did that answer your question?
Yeah.
All right. Other questions? Anybody get a number on this one? I didn't finish it. I just want to write down the numbers. I feel like it's complete.
Got him good.
we do number 47?
47. Do that. Let's see real quick. 47. Yeesh. I'll go back over here. While somebody's still calculating, I'll start writing the problem down. Okay, so did we ever get a number on this one? This one calculate. Okay. If you get a chance. Well, let's try this. I'll come back if I get the number. We'll write it down. Any suggestions on this one? Exactly. 3 is a constant, but then again, so is pi. So we could rewrite this as 3 pi I mean, if you wanted to, could you not factor out the 2 as well?
No, that's true.
Factor out that 2.
It's genius. Hey,
You don't have to, but you could.
this is looking
I think I
real.
will. Okay, so now we're doing 3 pi over 2 times the indefinite integral of 1 over x plus 3, evaluated from 1 to e minus 3.
What's it going to be? The natural log of x plus 3?
Right. Observe, that's correct. The derivative of the natural log of x plus 3 is equal to 1 over x plus 3 times the derivative of x plus 3. Don't forget that chain rule. But the derivative of x plus 3 is simply 1. So it doesn't affect it this time, but you should always be cognizant of thinking about that.
Mm-hmm.
If you left the 2 in there, you would have had to deal with it. But by factoring the 2 out, then I don't have to deal with it this time. So this is obvious going backwards now. So this is 3 pi over 2 times. And again, when we go backwards, we have to accommodate the domain restrictions, so we got to put that as a value on there.
Oh, yeah. Is that because of the natural log? Right.
The natural log has a more restrictive domain than the original function we started with. And we're basically done. 3 pi over 2 times log of, let's see, e minus 3 plus 3 is log of e. Log of e. And then put in a 1 is log of 4, looks like. Yes. So log of e is just 1, I guess. So that's 3 pi over 2 times 1 minus log. That's, everyone follow that?
Mm-hmm.
Okay. Well, I want to direct us onto a new section. It's going on that a little bit. We'll have some time on Monday. We can do some more of these if we'd like. We still practice on those. If you've gotten stuck on something and can't figure it out, we'll try again on Monday. Just for some more topics to cover, we discuss signed area versus absolute area and what it means. We just did, right here, we just did an absolute value function. What does that, a good leap what we're going to do today? With this in mind, if you give, I can leave the picture up there, I guess, but let's compare this, which had some result. Did anybody ever get a result on that one? Okay. And then compare that result to or whatever the number is. These two have numbers. Are they going to be the same numeric value? Expressions. So this one is going to be the red one. That one's going to be black one. So clearly the area under the black and under the red on that interval are different.
Yeah.
Okay. Under the black curve, you're going to have a good bit of negative area to counteract some of this positive. So this is called, as we've said before, this is called sign area.
Oh.
As we said before, and we tied it back to velocity and position by saying, if you envision this as v of t, then we call this signed area the net displacement.
Got him.
Okay? That's what we've said before. So the definite interval gives us signed area because we're dealing with Riemann sums. Riemann sums give signed area. If you visualize this function as velocity, then as we showed before when we introduced all this, then the value of this definite interval is usually the net displacement. How much position change should I have from beginning to end? But the other one up here with absolute value, once again, because it's absolute value on the function, as we just went over, that's giving you an all positive function, so the area is all positive. We're going to call this the absolute area. So in some sense, it's more of what you think of as area, because the absolute area would be how much, if you were going to paint, if you had to buy enough paint to cover the square inches of this, then you would have to include the area here, plus the area there, plus the area there. But you would want that to be a positive area. Because otherwise, if you do signed area, you're going to subtract some negative area off, and then you're going to come up with not enough paint. But if you count it as positive areas, then you've got the total, what I would call paintable area. That's called absolute area. Now, in terms of velocity, if you think of this function in here as velocity, once again, it's like we did here, it's no longer called net displacement. Any guesses what that might be called?
Net velocity.
Called the total distance that we've walked. So we're calculating, because you can walk forward and back and stuff. So this would be the total distance. I'll remember that terminology.
Yeah.
So, again, if I start here and walk forward and come back to there, then I have a net displacement of 0. Right? I have some total distance I've got covered. So how would I see that again? You know, take a simple walking path like we've done before. And we're going to graph velocity. So if this is my velocity function, just one more time, let's suppose that my velocity walk was like this. This is A, and this is B. So what would that walk look like if I had to walk that walk? That's my velocity function going way back towards the beginning of the semester. What would that look like? I'm going forward at a fast velocity and I'm slowing down to a stop, and I'm going backwards and speeding up until I get to the same position I started at. I would walk forward, slowing down, then I would start back, speeding up, and then I'd stop. Because the area in here and the area there are opposites, the total signed area is 0. What would that mean about my position function? If I graph my position function now based on this, now I'm going to graph position. What can you tell me about the position function?
Is it a parabola?
It has to start and end at the same position.
Oh.
Forever. I mean, it could have been starting at 0, but I could have started at 3. So it has to be something like, whether it's a parabola, probably a parabola, but even if it's not a parabola, I know it has to start and end at the same position because the net displacement is 0. But even though the net displacement is 0, I started and ended at the same position. I actually walked some distance. So I walked some feet forward and some feet backward. So since if instead of these two separate as positive and negative, if you made a graph like this, which is going to be the absolute value function, now you got positive area on both cases, and that's going to give you the total distance that you want.
Nice. I dig it.
You just exactly.
Okay? Does that make sense now a little bit? Okay, so that's called, in the book, and we're going to go with that same terminology. If you don't have an absolute value symbol on your function, then it's going to give you signed area, and that's equivalent to talk about net displacement. If it has absolute value on it, or if you put absolute value on it because you need to for some reason, then you're getting absolute area, which is all positive area, and that's going to give you total distance traveled. Okay, that's pretty straight up. Next thing up, area between two curves. Instead of area between a function and the x-axis, what about the area between two functions? So if I want, let's see, graph a couple of functions here. So here will be one function. This is y equals f of x, we'll call it. And then we'll put another function. Y for g of x. If I want the area between those two functions, so the area between f of x and g of x on the interval from a to b. So graphically, what would that what would you think I'm talking about as the area between the two functions? So it would be area here. What's the area? There, you all agree that's the area between the two functions?
Yes.
So how do we calculate that? Well,
You gotta subtract integrals or something.
yes, we're going to subtract integrals because you could find the area under the green curve down to the x-axis with an integral. And then you could find the area under the red curve down to the x-axis, and then you could work with those to calculate the area between. Or we'll just write it this way, quite simply, make our life a little easier.
Okay.
The area between these two curves is the definite integral from a to b of the absolute value of f of x minus g of x.
You enjoying yourself?
So we don't just put, we do need the absolute values on this one. Why do we need absolute values?
Because we're looking for the total distance or something.
Looking for
The
you.
absolute area.
We're looking for the positive absolute area. Plus, this, if I just subtract f minus g, think about what's happening. Up here, like, instead of making rectangles, the idea of this is instead of making rectangles all the way down to the axis, I'm making rectangles in between the two curves. Can you visualize that? If I do f minus g, then I'm getting a positive rectangle when I'm in this left-hand region. And over here, I'm going to get a negative rectangle. So by putting absolute value on f minus g, I'm making all of them become positive. So I'm getting absolute area between the two curves by this process. Are we clear on that?
Yeah. Mr.
Oh,
Gaddis,
quick
I have a
question.
Okay, with that function right there, and you're calculating the area between it, would you have to consider it in two separate parts? Because at one point
Exactly.
f... Okay.
Yes. So on this one here, if I was going to do this problem, if I was given an actual function for f and g, then I would have to figure out, good observation, I would have to figure out that point there, we'll call it C. How do you figure out that point C?
You gotta find an intersection between the two
Yes.
functions.
So you're going to say that at C, f of C has to equal g of C. Those two functions equal each other at point C, right? So they cross, they're intersecting. And solve and get, that will give you C is equal to some number. Then you can do this as integral A to B, and in the first, from A to C, F is the big one and G is the small one, so it's positive. F minus G is already positive, so I'm just going to do F of X minus G of X, dx, and then plus, that's just C, and then integral C to B,
Yeah, hang on.
and I
Let's
do
look
the negative of F of X minus G of X.
I think I know that.
Because from C to B, G is the big one and Y is the small one, so I'm going to be, when I subtract F minus G, I'm getting a negative, so I got to take a negative of it and make it positive.
Is that how you
That's not too bad to do. You just do that, and you just have a given function. I mean, like, the book has examples. You should be able to do that. It's not too bad. We just did one where we found the the places where not intersection points. We found the places where we had to change. We just did one like that. The only extra step now is finding the point of intersection. Well, to find the point of intersection, you just do this. You understand?
Okay.
You got to find that first. Question? Reza?
Is it possible to have more than one C?
Yes. If you look in your book on page 377, there's a picture of two functions. They even tell you what the functions are, so you can take a look at it. 377. The blue curve on 377 is g of x equals x squared, and red curve is fx equals x plus 2. And the line x plus 2 intersects the parabola twice. So there would actually be 2 points there. And you could have even more. What if it was a cubic function? You know, and you could have lots of intersection points.
So would you just add more definite integrals to that thingy?
Yes, you would. Yes, exactly right. You would keep splitting it as long as you're within the original interval. What if my intersection point is outside my interval? Like, you don't understand that? Suppose there's one function, and here's another function, but the interval I'm worried about is here.
It's a Jesus fish. An ichthys.
Well, since the intersection point is outside of the interval I'm interested in, then I don't care. You understand? So you would find the intersection point, but if it's not inside the interval, then you don't do anything with it. So yes, every intersection point within the interval you're concerned about has to be a split point. Okay, next up is called average value of a function. So average value of a function. Go back over here. Let's give a simple example to talk about this.
Lag.
So I'm talking about average value of a function. How do you find average value in general? Add up the values and you divide by the number of values you add. In general, average is equal to the sum of some numbers, some values, divided by the number of values. So on this function, I can approximate this average value. So in this function, I can say the average is approximately equal to, and I could do maybe, how about a right sum with 4 intervals? So, you know, I do 1, 2, 3, and 4. So then I would have a function value there, I would have a function value there, a function value there, a function value there. So I could do the sum of k equals 1 to 4 of f of x sub k, and then divided by 4. So that would just be f of 1 plus f of 2 plus f of 3 plus f of 4 divided by 4. And f of 1 is 1, and f of 2 is 4, and f of 3 is 9, and f of 4 is 16 divided by 5. And whatever that is, so what is that? 10, 14, and 16, 30. So 30 over 4, 15 over 2.
Isn't that just for a Riemann sum, though?
It's almost a Riemann sum. Good observation. Exactly.
But
So
how can
what
you
we're
divide?
saying-
How can you divide
It's on the
infinity?
interval 0 to 4.
So I have approximated my average value as 15 halves, which is 7.5 or so. So with this, I've approximated it. So this is at 9. So 7.5 would be like maybe right there. So this is my average function value is at 15 halves. as an approximation of the average value of that function on 0 to 4, the average height of the function. It's not always at 15 halves. It's at 15 halves only one time, but on average, there's heights all over the place, but we're saying it's an approximation. But that's only an approximation with 4 values. How many different values are there really on this function between 0 and 16? There's infinite different values. So we need to somehow bring in the idea of infinite different possible function values to get the true average. Well, so what we'll do is we'll say that the average value equals
1 over b minus a.
N goes to infinity of the summation of k equals 1 to n of f of x of k. We can call it a star just to feel like it. Then we got to divide that by n. I'm just doing here what we had right there. The sum of the values divided by n gives me the average, and we're going to do the limit as n goes to infinity so that we get all of the values, not just a few of them. And that, as Teresa suggested, looks a lot like a Riemann sum. It's not quite a Riemann sum. Why is it not a Riemann sum?
Why?
Because it's x, right? What if by algebra magic, I went over here and said, sorry, what's that reason?
I said I call it sorcery.
Oh, sorcery, yes. Algebra sorcery, yes. Or voodoo or something, yes. So I'm going to multiply by b minus a over b minus n. I do that? Yeah, that's because that's 1. I mean, b minus a is 1. If you put b minus a over b minus a, you're getting 1. Okay. Why would I want to do that?
Why?
Now you have the delta x on top.
What is b minus a over n? That's delta x. Now I have
That's
it goes to infinity of summation k equals 1 to n f of x of k star times delta x over b minus a. What is the limit n goes to infinity of the summation k equals 1 to n of f of x of k star times delta x equal to? What is this numerator with the
Yeah.
yeah, that's just the definite interval from a to b of f of x dx divided by b minus a.
could be multiplied times 1 over b minus a.
Or it could be multiplied by 1 over b minus a if you would just insist on that.
That's what the book said.
Now, what the book is, sometimes it is
The book is what?
yes, multiplying by 1 over b minus a is equivalent to dividing by b minus a. I will concede that sorcery. Okay. So what is that really saying to me? To find the average, remember what we're finding, the average function value. That means we're finding the average height, think about that, the average height of the function. And it says to find the average height of the function, you simply take the area under the function divided by the width. Think about that.
Oh my gosh.
Average height is equal to area divided by width. Oh, really? I didn't know that. Width times height makes area, doesn't it? That's how we calculate area in the first place. So
Yeah, that's crazy.
This is great.
that is
Wait, I
amazing.
got a question, Mr. Gaddis.
Yes, Reza.
That limit, is it part of the fraction or is it off to the side?
It's either way. The limit does not affect, because the limit is only affecting n, it does not affect b minus a.
Hmm.
Right? So it doesn't, Technically, it's included. It's a good question. Technically, the limit is on the whole thing. I was a little sloppy in my sorcery because it does not affect the b minus a.
Yeah. So how do you have the definite integral on top then? Wouldn't it be the definite integral of the whole ratio if that were the case?
Yeah, the limit is on.
Well, yes, but once again, this factor is a constant, so it can come out of the definite integral.
Oh, so what you're saying is 1 over b minus a is a good idea.
Sure, that's a good idea. Okay. So for Rezo, we'll write it as 1 over b minus a times integral a to b of x.
That's what the book has.
Right. Now, there is one last theorem that's related to one we've seen before. It's called the mean value theorem of integrals. Mean value theorem of integrals. On page 379. So it's going to look to me a lot like what we've seen before, but yet maybe not. It says if f is continuous, so if f of x is continuous on, can't spell today, on a to b, and there is a c value where f of c is equal to integral a to b x dx over.
So is that just saying that if it's continuous, then an average value exists?
It's saying that there is a c value where the there's a c value. There's a special c value that I can find that generates that average height.
Okay.
Well, I mean, it's kind of obvious. There's a c value. If I calculate my average height on this one, let's go back and do this one. Let's do it on here. Do this one. Okay. So one more time with the one we've got. So we've got f of x equals x squared on, and I did 0 to 4. So it says that on that interval, 0 to 4, there is some c value. So there is some c value that equals the integral of 0 to 4 of x squared dx over 4 minus 0. So f of c is equal to 1/3 x cubed from 0 to 4 over 4. So f of c is equal to 64 over 3 over 4, 16 over 3. What does that mean graphically for me? Graph. Let's go back over this graph. So let's make a quick sketch one more time. So we got some kind of parabola shape here. There's 4. I guess that must be 16. That's 0. And if we take the total area under this curve, so the total area in the curve is this integral, definite integral, was 64 over 3. So the area under this curve is 64 over 3. That's what I've seen so far, right? And I've got a width of 4. So I've got a width equals 4. And it says that there's an average height the average height is 16/3. This is my average value right here. This side is average. That's what we just calculated right here, over there. We calculated average value. So this is average value. This is my average function value. At 16/3, so where were 16/3 was at 5 1/3 or something like that. So somewhere in here is the 16/3 is my average function value.
Nice.
If I now, what's really being said here is, if I now draw a single rectangle at that average value, the area under this green curve is equal to the area under the red.
Oh, wow.
In other words,
Interesting.
if everyone was shooting a 16/3, then your average is 16/3 and your total area is the same. Or if everyone's shooting different numbers and you add them up and divide by n, the average is 16/3. So either way, we get the same area underneath this curve. So this area here in the green curve area is still 64/3.
Wow, that's awesome.
Furthermore, there is a number C right there, so that the function value at C is equal to this height. Can I find that C value? Sure. So I want f of C equal to 16/3. What does f of C mean? Well, f of x is x squared, so this must mean C squared is equal to 16/3. C is equal to plus minus root 16/3. But we're only dealing with 0 to 4, so we're not even going to, we're going to ignore the, so on 0 to 4, we're only going to use the positive root 16/3. So this is my number, root 16/3 right there. At that location, you can draw, if you draw a single rectangle that hits the function curve at that location, the height of it will be the average value of the function, and the area under this single rectangle will be the same as the area under the function. And one last comment. This is the mean value theorem for integrals. I wrote it this way, which is different than the book. The book has 1 over b minus a in it because that's the way they wrote it up here. I wrote it this way on purpose because I wanted to say one more thing. What's the fundamental theorem of calculus say about this numerator up here?
It's the subtraction of the antiderivatives at the endpoints. Ooh. Ooh. Ooh.
Doesn't that look a lot like, what does the original mean value theorem say?
Oh my gosh, it's so close.
F times C equals f of b minus f of a over b minus a. Okay, well, okay.
That's awesome.
This is, see, this it's the same thing. I don't know if you realize. It's identical because this
Scroll it up a little.
is derivative. Okay, yeah, up here in the original mean value theorem, we had f prime of C is equal to f of b minus f of a over b minus a. Here we have little f of C is equal to capital F of b minus capital F of a over b minus a. But the point is, little f is the derivative of capital F. I mean, this is capital F prime.
This is like next level sorcery right here. This is great.
That's sorcery, that's for sure. Okay. It's about all
You know,
time.
when you figure out how to make gold out of lead,
That's.
you got 5
that's-
minutes.
5 minutes to come up with how the alchemy, how to make,
It's not quite
you don't know,
sure. More
flake of
alchemy
gold out of a
course,
whole
right?
pound of lead after hundreds of years spent.
A lot of
trying to
calc
do that.
tips.
No one was able to figure out how to do that. You'd be rich if you could. Why would they want to do that? Because why? Lead's abundant and gold is not. Gold was more valuable because it's abundant, not abundant. Supply and demand. Lead.
But that would throw havoc in the economic cycle.
That's
Because
right.
suddenly if there's an abundance of
So-
gold,
so it was-
scarcity no longer
It
applies.
was fortunate sorcery that they couldn't figure out how to make gold out of lead. We didn't disrupt the whole, we didn't
just
destroy
close
life,
it.
as I said yesterday. You have a question or anything?
Well, no, I was just adding on to your economics discussion, saying that
Okay.
they would cause inflation in the gold market.
I'm sorry? Something in the gold market?
Yeah, you would cause inflation in the gold market. So you have to do alchemy to bring it back.
Right. So that's when you hoard it and stick it in the basement. That way it brings a. Or do you just oversupply it? That brings down the inflation. Which one is that? I'm not.
Yeah.
You-
Anyways, if you're figuring out how to make gold out of lead, please let me know. I'd like to be a partner in that venture.
Depends on the capacity of that particular.
Yeah, exactly. Well, that's right.
Yeah.
That's just. Man, okay. Well, you have some homework in section 4.6, which is what we just covered. So over the weekend, be sure to do the homework in section 4.6, and once again, keep practicing on doing definite intervals, which now we're applying the definite intervals in some new ways that fit, including area between two functions. So more and more practice makes it easier to find the antiderivatives. All right, see y'all on Monday. We have a test a week from today on this block material. We've got one more section to cover. Then we have the test. Have a good weekend.
Yeah, it's not that much.
It is Thursday. It's Thursday, Friday.
But we have some. You'll be solo. You'll be solo today, actually.
Yes.
It's
She didn't pay attention.
online thing for.
I asked her question.
I did. And it said something about substituting you stuff.
Yeah, I was gonna point that. That's honestly the first thing we do in Calc 2 is use substitution,
So
which
I
is
can
a
give it to you that day.
more formalized way of finding the antiderivative. So we're finding out that guessing and checking.
Okay.
Have a good weekend.